Hello, everybody. I am Mahsa Nakhostinrouhi, and I'm a researcher at GFZ Institute in Potsdam, in Germany. I'm going to talk about exploring the key visible near-infrared and shortwave infrared bands regarding the prediction of nickel in soil in an urban soil using explainable AI. Nickel is a chemical element, as you know, which can be easily elevated in an urban soil due to a variety of sources. Pollution sources like transportation, industries, road work, and waste disposal. So this increase in nickel in an urban soil has a lot of disadvantages. For example, it can be easily taken by plants and then affect human health and maybe other living organisms. So what method is common regarding measuring and analyzing nickel in soil is spectrometry data. And there are two main challenges regarding this data when we talk about nickel. The first one is that there isn't a specific spectral signature for elements like nickel. And it makes us to use some methods like machine learning ones to analyze this element. However, these methods are black box, and it makes it difficult to make them interpretable more. So the solution used for these challenges in this study was exploring the feature importance regarding the prediction of nickel based on explainable machine learning methods. We chose Berlin as our study area, and you can see the distribution of the 89 soil samples all over that, mostly in the vicinity of the transportation regions. Like every soil study, we started from collecting soil samples and preparation them, and then transferring them to the spectrometry laboratory in order to measure their visible near-infrared and shortwave infrared spectra. On this slide, you would see a diagram of the methodology, and it starts from collecting data including nickel, which was measured for all samples, and also the spectral data measured in the spectrometry laboratory. And then there was the data pre-processing step, and then training, splitting the data into training and test, and using the training data in order to train a random forest model, and also grid search CB method in order to optimize its hyperparameters. And finally, the test data was used to measure the prediction of nickel in unseen data, and then they were used to validate the model based on some error metrics. And at the end, the best model was chosen, and it was used to find the most important spectral features regarding the prediction of nickel based on two methods, including mean decrease in impurity and permutation. The first results are shown in this table. It includes the descriptive statistics for nickel and some other soil properties, and we used them. For example, one of the most important information was the skewness regarding the nickel, showing us that we had to use some transformation, like logarithm transformation, to make it to more close normal distribution. This slide includes the reflectance spectra in the left side for those 89 soil samples and their absorbance as the right plot. Here you would see the plot showing the validation of our random forest model for prediction of nickel based on test data. And as you can see, the R-square measured was 0.78, which could be somehow acceptable for nickel in soil. And this slide provides the results coming from explainable machine learning in two plots. The plots in the left side shows the result coming from MDI method, and the result from permutation method is in the right side. In order to make it more clear, I have zoomed on them on this slide, and you can see 10 most important spectra regarding nickel's prediction based on two explainable machine learning methods. And you can see that based on MDI, mostly the spectra related to the shortwave infrared were the most effective ones, while the permutation method chose both shortwave infrared and also visible infrared, like 401 or 3 nanometer as the most important features or spectra. In order to know the reason behind the results coming from explainable AI, we calculated the correlations between nickel and some other soil properties which have the direct spectral features like humus, clay, pH, aluminum, and Fe. And this heat map shows that there are almost high correlation between nickel and aluminum and Fi, in fact more than 0.70. So it can be the effect of aluminum and Fe or iron, mostly leading to that result from explainable AI methods. This plot is also coming from a study of Sheila Katoval in 2018. It's a plot showing the spectral signatures of a variety of soil samples, and it shows that what are the most important soil samples regarding each part of the visible near-infrared and shortwave infrared spectra. And as you can see, iron oxide is determined in the visible infrared area regarding 400, and aluminum hydroxide is shown the reason of absorbance spectra and shortwave infrared around 2000 blah blah nanometer. So it can be somehow a good proof to the results coming from our explainable AI methods. So based on the results, we got these kind of conclusions in this slide, and it was the first one, the high amount of nickel in a traffic region of an urban area, which we found it. And then it was the capability of random forest method to model nickel in urban soil, and then it was 2 parts of spectra, including shortwave infrared and visible infrared, regarding the prediction of nickel as the high important parts of spectra. And finally, it was the high correlation between nickel, aluminum, and iron as the reason behind the results coming out. So that was all from my side, and thank you for your attention, and you can get in contact with me based on these addresses.